Hi, we're going to start talking about topic 7C, which will be the solutions to Schrodinger's equation for translational motion. So the most important part of this really is you're going to see exactly what it means to solve Schrodinger's equation, and you're going to see exactly what it means when they say that the boundary conditions force the energies to be quantized, force you to only allow some energies. So okay, so topic 7C. See if I get a little more central. So the key idea is that particles in free motion, where they never run into anything, don't have quantized energy. But as soon as you put restrictions on where a particle can be, you're going to see that that forces us to see those discrete energy levels as the only possibilities. So rather than go through the way the book does it, I'm just going to solve the problem with you on a separate sheet of paper. So first we'll define our model. So the particle can only move in one dimension. So we'll call that the x dimension. And it's in a box. So sometimes this is called particle in a box, in a 1D box. So when you're at either 0 or L for your x values, the potential energy goes to infinity. That's the same thing as thinking, if this was a baseball inside of a box, when it hits these walls, let's say they're made out of concrete. So it's absolutely impossible for that baseball to go through those walls. So there's an infinite potential energy that holds it within the 0 to L region. So we have 3 different regions. In region 1 and in region 3, so potential energy goes to infinity and stays at infinity forever. So outside of x equals 0, potential energy is infinity. And when you get above x equals L, it's also infinity. But when you're in the box, there is no potential energy. So that's a lot like thinking of maybe the box has a gas molecule, a perfect gas molecule, and flies around. Maybe there are more gas molecules in there, but they don't interact with each other when we call things perfect gases. And so there's never any potential energy of interaction as long as you're within the region 0 to L. So we want to solve the quantum mechanical problem for this translational. So this is a model for translational motion. So in regions 1 and 3, the Schrodinger's equation is going to have the kinetic energy part. So negative h bar squared over 2 times whatever mass of the particle is. Second derivative with respect to our function with respect to x, plus the potential energy in this region is a constant, and it's constant at infinity. So the equation we want to solve when we're in region 1 and 3 looks like this. So we can use that to show, we're going to need Euler's relationship a little bit later, so it's just there so I get it right. So we can take this and we can rearrange it. So we have infinity times psi and E times psi. So let's take those on the same side. So then we'll have e minus infinity times psi, and the second derivative with our constants. So we can simplify that. E minus infinity, no matter what e is really just negative infinity. So we'll get negative infinity times psi, and that will cancel with this negative. So we'll end up with h bar squared 2m. Okay, so now we want to look at what the second derivative is going to be. So, or what psi is going to be, sorry. So we take infinity back over here. We essentially have the second derivative times 1 over infinity equals psi. So anything times 1 over infinity is times 0. So that means psi in regions 1 and 3 has to be 0. That's the same thing as saying the particle can't get out of the box if the walls are infinitely high and infinitely thick. So now we're ready to look at inside the box when v equals 0. So that we called region 2. So we're going to have negative h bar squared for 2m. But now v of x equals 0. So the second term just goes away. And what we're solving is negative h bar squared over 2m times the second derivative gives us back a constant times the function. And you know what functions work there or are solutions. So sine works. If you take the first derivative, you get cosine. Second derivative, you get sine back. So sine will work. Cosine will work. The exponential function will work because you know when you take the derivative of it, you get that function back. So we want to start out with a wave function that's a combination of every mathematically acceptable solution. So that's why I had Euler's formula here. Sine and cosine can be written as linear combinations of the exponential function. So because of that, if we include sine and cosine, we're really also including this function. So we don't have to include sine, cosine, and exponential because they have a dependence on each other. So I'm going to start out and I'm going to say psi equals a sine kx plus b cosine kx. And now we'll look at how we can simplify that based on the physical properties of the system. So this is the mathematical solution. We want it to be complete at this point. We want it to include every possible mathematical solution there is. But now we want to think about what our boundary conditions allow. So we look at our box again. And what we saw was in region 1 and 3, the wave function is 0. So that means when you hit the wall, the function has to be continuous in order for Born's interpretation to make sense. So remember, we can't have it starting up here if it's entering on this side. So when you get to x equals 0 and x equals L, psi has to equal 0. So if we look at our solution, these are our boundary conditions. So the boundaries where we know what the values have to be. So the first one is pretty easy. When we look at x equals 0, the function has to be 0. Sine of 0 is 0, but cosine of 0 is 1. So that tells us that this first boundary condition that means that you can't have any contribution from cosine. So because cosine of 0 is 1, that means b has to be 0. We can't have the function with a value other than 0 when we reach x equals 0. Sine of 0 is 0, so that will work. But we have the other boundary condition. So we have the boundary condition at x equals L. So now we need to say that has to equal 0 when we're at x equals L. And so that puts restrictions on what values k can have. Sine of any integer value of pi is going to be 0. So where n equals 1, 2, 3, 4. Can't have 0 because if we had 0, then the wave function would be 0 everywhere. And then if that was true, then there'd be no probability of a particle. So we have to start with n equals 1. So that means that KL has to equal n pi. And so you can solve for k. So k has to equal n pi over L. So our second boundary condition has restricted what values of k we can have. We can't have every single value of k. It can't be continuous. So now we have almost specified the whole function. So now we have psi equals a sine, and our k can only be n pi over L. And so that's our wave function to this point. We also need to know what a is. A can't just be a random parameter. We have to define it in terms of properties of our system. So the other thing we know is if psi squared is proportional to probability of locating the particle, if we add that probability up over all the possibilities of space where the particle could be, that has to equal 1 because we only have one particle. So that means particles can only be between 0 and L, but it means if we take a sine of, I'm going to do it for the n equals 1 value, but you will see, actually, well, let's do it this way. We can generalize it in a minute. So if I square that function and integrate over all the possibilities, has to equal 1. So I am going to do that integral on Mathematica, just so we start getting used to that. So I'm going to bring Mathematica. And I'm going to stop the share because I don't think it goes straight to the other screen. I'm going to put in a new notebook. Okay, so you're going to learn Mathematica better if you already know it, and you're going to learn it for the first time if you don't know how to use it, because you just don't want to do these integrals yourself. There would be a lot of integration. So you can use this palette and write it like calculus, but you'll also learn in the computational physical chem book how to do it with commands. So I'm going to pick this, and my lower limit is 0. My upper limit is L, and I'm going to integrate a function. So the function is sine, so it starts with a capital S. The argument goes in a square bracket. So sine of, going to pick pi off the palette, so I know that it's for sure pi. Oh, that's why. Okay. Okay, there it is. Sorry. Pi. You can also just type capital Pi. So it'll be pi times x, and I'll put parentheses around those two, divided by L, and then close the argument. I want to square it because that's our wave function, and I'm integrating over x. Oops, and I told me immediately that I forgot a parenthesis. Okay, and it tells me that that integral equals L over 2. So it equals L over 2. Let me put my A in here. Well, if A is, I'll put it here to make sure that you understand what I'm doing. Yeah, so the integral equals A squared over, or A squared times L over 2. So that means and it should have been a capital A. Mathematica doesn't care, but I'll put it in as a capital A so that it looks consistent with what I'm writing. Okay, so A squared L over 2 has to equal 1. So that means we rearrange that. A has to equal, whoops, no, I've got to stop the share and go back to the screen, sorry. Yeah, so our integral that we did has the value of A squared L over 2. We know that has to equal 1 in order for the probability to make sense, that when we add it over all space, it equals 1. That means A, when you rearrange this, has to be equal to 2 over L square root. So now we have our entire wave function. We have 2 over L square root sine of n pi over Lx. So we've defined everything. So now we want to figure out what the allowed energies are. When we had to make this restriction that only integer values of pi worked, that also restricted our energy. So let's just make sure that we can make sense out of that. So what is the energy? So in that region, where the particle exists, the Schrödinger's equation says that negative h bar squared over 2m times the second derivative is equal to E times psi. So when we look at what our psi is, so if psi equals we can figure out what the possibilities for energy are. So if you take the first derivative of psi, you get the derivative of this is cosine, but it's also n pi over L. So the derivative of the angle times cosine. Then the next derivative, so this is the first derivative. So if I take the derivative of this, I get 2 over L to the 1/2. I get all of this stuff squared because I have to take the derivative of the angle again. And you could have Mathematica do this. I just feel like for a lot of derivatives, it's easier to do it yourself. And then the derivative of cosine is minus sine. So I'll put that there. And that's what we get for the second derivative. Sorry, it's getting off to an angle. So now we want to group things so that we have the wave function separate from all the other constants. So this and this is the wave function. So what we end up with on the left-hand side is negative h bar squared over 2m. And then when we multiply it by the derivative, we get negative n squared pi squared over L squared times psi. That's the left-hand side. And then the right-hand side is equal to E times psi. So all of this represents the allowed values of energy. So when we group all these terms, the negative will go away and we'll end up with n squared. So the only certain energies are allowed. N squared, h bar squared, pi squared over 2m L squared are the allowed energies, where n equals 1 to integer values up to infinity. Your book simplifies this, so if h bar is h over pi, if I put that in here, then the pi's cancel. So if I plug that in, I get n squared, h squared, pi squared, and h over pi squared cancels the pi's. And then we get, why do we not have an 8? That should be 8. Where did I drop a 4? Oh, there's a 2 here, that's why. So the pi's cancel, but you get h over 2 twice. So you get h over 4 times 2 gives you 8. So we have the wave function defined and the possible energies. So the wave function was defined using the boundary conditions and the solutions to this ordinary differential equation. And because of that boundary condition at L equals, or at x equals L, that the function had to be 0, we ended up only being able to use certain angles in our sine function. So that's where the energy became quantized, essentially. So that's a complete solution to Schrodinger's equation for a pretty simple problem. But there really aren't solutions we're going to see to very complex problems. So in order to see what's going on, you really have to work on a very simple problem that you can understand. So now let's go back. So we've gone through all of this. We normalized the function, came up with the energies and the wave functions, just like your book did. They did it slightly different than I did it, but same exact ideas. This talks about the energy difference between two states, and we'll use that in a problem. And this talks about the solutions. Do they give us pictures? Oh, yeah, they do. So here they show us what the wave functions look like. So when n equals 1, you have just 1/2 of a wave in between 0 and L. When n equals 2, you're going to get a node in the middle. N equals 3, you'll get 2. N equals 4. So each time you go up, the energy has, or the particle has more energy. The second derivative is bigger. There's going to be more kinetic energy. So second derivative being bigger means you have more oscillations. But if you keep going up to the point, so let me say something first about the ground state. So when you're in the ground state, this says the most probable location you're going to find the particle is right in the middle of the box. That doesn't really make sense classically, because if you have a particle in a box and there's no potential energy, you should have an equal probability of finding it anywhere in that box. But quantum mechanics says in the ground state, you're going to have a higher chance of finding it in the middle. In the first excited state, you're going to have a high chance of finding it to the left or the right. a node in the middle where there's 0 probability. As you go up, the states get with more and more oscillations. And what happens is the ground state, you had a high probability in the middle, but when you're in a very excited state, it's just oscillating and oscillating. So essentially you start looking like you have an equal probability of finding the particle anywhere in the box. And that's what classical mechanics would tell you. So it's a concept called the Bohr correspondence principle, that when you get to excited states, things start to look more classical. So this model is not perfect for anything, but there are a few real systems that it's a pretty good model for. So self-test 7C.1, you have a proton caught within a nucleus, and it wants you to calculate the energy of the first excitation. So that would be going from n equals 1 to n equals 2. So we have a proton. It's in a nucleus, which is really small, so it's confined within the regions of 1 times 10 to the minus 15 meters and 0. So in 1 times 10 to the 15 meters of a box, essentially. Infinite boundaries, so impossible for the proton to leave the nucleus. So if we want the first excitation energy, we want the energy between the n equals 2 state and the n equals 1 state. So if I take the difference between those two, when n equals 2, then it's n squared. When n equals 1, it's 1 squared. So it's going to be 4 minus 1 times all of these constants, because they each have the same constants. So it ends up being 3 times h squared over 8ml squared. When I put those into that equation, I end up with 0.6 giga electron volts. And a giga electron volt, the problem tells you, you wouldn't have to give it in those units, is 10 to the 9th electron volts. So that was this self-test right here on page 335. Now we're going to go into a concept that's really interesting, tunneling. You've probably heard of tunneling in some way or other. Essentially, it's the concept that a particle can be someplace it doesn't have enough energy to be. So if we look at this little picture they have up here, let's focus in on it a little better. We're talking about a particle. So this particle on the left-hand side of this wall is oscillating. It could go back and forth. Well, no, it can't because there's no wall over here. So it can hit the wall, and the wall has some energy. So it's a wall that doesn't have an infinitely high potential barrier. It has some finite barrier, and it has some finite width. So it's different than the particle in the box in those two ways. Finite height, finite width. So the particle could bounce off of that wall, but there's a probability that it can go through that wall and end up with oscillation on the right-hand side, which would mean the wave function exists on the right-hand side. You have a probability that that particle went through the wall, even though the energy of the particle, shown here as at the black height, is lower than it would take to go over that potential energy barrier. This problem is a challenging problem, but it's exactly like the last one. You can look at the different regions to the left within the barrier and to the right of the barrier. You can solve it like we did with the particle in the box, inside or outside the box. And then the big thing is, then you have to get the waves to line up so that they have the same value when it's coming in and when it's inside, and then when it's inside and when it's leaving. Also have to get the derivatives to equal each other at those points. And when you do that, you get this complicated equation here, which I'm going to use this simplified one because that equation has a lot of variables in it. Oh, there we go. That's better. Okay, so the exact equation is this one here, but if the V and the E aren't too far apart, this one will work. So the tunneling probability, so that's the probability that the particle gets through the barrier, is defined by this equation. So we're not going to solve it. It's no more difficult to understand than the particle in the box, but it's actually kind of hard algebra to get the boundary conditions satisfied so that the waves and the derivatives are equal at the walls. So let's look at self-test 7C.2, which is on the next page. So it's on page 336. It tells you that it tells you that we have, what particle? We have an electron, and it has the energy, electron with energy 1.95 electrons volts. The height of the potential barrier is just a little bit higher than that, so the particle shouldn't be able to get through. It has a height of 2.00 electron volts, so that means the potential barrier is higher than the energy of the particle, and we're going to see that the particle has a probability of making it through. The height of, or the width of the barrier is 100 picometers, so for 100 picometers you have that potential energy. So we're going to use the tunneling approximate equation, and it says 16 times this thing called epsilon. Epsilon is the energy of the particle divided by the potential energy. W is the width, and this kappa is 2 times mass of the particle, and then the difference between the potential energy and the energy of the particle divided by h bar. So for this one, epsilon will be the energy of the particle divided by the potential, so 0.975. So 16 times 0.975 times 1 minus 0.975 multiplied by e to the minus 2 times kappa. When I calculated kappa, I got 1.145 times 10 to the 9th, and I'm just using everything in SI units. And then the width is 100 times 10 to the minus 12 meters. So I got a kappa of 1.145. Oh yeah, the width doesn't go in there, the width goes in here. So kappa and then times the width. And I've done this problem twice and I keep getting 0.31, whereas what they get is 0.881 as a probability. And the only thing I can think is they use the more exact equation. So you could try that, but that more exact equation is very gnarly to work with. Okay, so now we're going to talk about the last idea in this section of the focus, which is what if I have more than one dimension? So what if I have motion in 2 dimensions? So similar to what we had, but now we have a particle in a 2-dimensional box, so it can move on a surface, and you have some length of the box in the x direction and some length of the box in the y direction. And so if I write, maybe we'll be able to see this. Yeah, I think I'll write it. It'll make it easier to follow. So we want to see that we already know the solutions to this. So we're going to have the same initial problem. It's a particle in a box, so we know can't get outside the box. But inside the box where the potential is 0, we have the kinetic energy in the x direction and the kinetic energy in the y direction. So and this would be EK in the Y direction. So I want to see that you can separate this essentially. So I'm going to go through this process of separation of variables because this is really, really a critical point. So yeah, on page 338, they talk about partial differential equations. So a differential equation that's a function of more than one variable, the function. So we did one where it was just x, but now the function is going to be a function of x and y. So it's a partial differential equation. Most of these are impossible to solve. But if you can separate the two variables, then you can solve them. So let's look at how you might do that. So our function is a function of x and y. First thing you're going to assume is that I can write that function as a product of two functions. A product of a function that's only a function of x and a function of y. And we'll show that that was a valid assumption. So when we look at each of these terms, if you take the derivative with respect to x of this function, then the y part is just a bunch of constants. So what you're going to end up with is and it's also true for taking the derivative with respect to y, then the x part is a constant. So then we can say so the next step is to get all the x's and all the y's separate of each other. So if I divide through by the function, then we end up with, you divide through here, you get y over y, so you end up with 1 over x. So you get negative h squared over 2m, 1 over the x part of the wave function times that second derivative. And when you divide this, then you have x over x canceling, and you get and so you get these two terms both have to equal a constant. So the argument goes that if x changes and y is held constant, then e can't change because the sum of the two has to be equal to a constant. So you can say that this guy is equal to a constant, and this guy has to be equal to a constant. So if y changes, this whole thing has to stay constant because this would be constant. And if their sum has to equal a constant, then each term has to be a constant. So each of those can then be written as a separate that one's equal to a constant, and we'll call it the energy in the x direction. The other one has to be equal to a constant. And so these are exactly the same differential equations we already solved once. So this one says negative h bar squared over 2m d squared x. So I just multiplied both sides by the wave function that's only a function of x. So when you look at each of these equations, what they really are is just two separate equations for the particle in a box, one dimension. And because you could separate the variables, you can solve those separately. So that means that psi is going to be equal to x times y. And so it's going to be equal to times. So those two multiplied will be the wave function, because that's what we assumed back here, that you could write it as a product. And the energy total will be equal to the sum of the two. Oops, can't do that right yet because we didn't say it was a square box. So we have to say nx squared h squared over 8ml squared plus ny squared h squared over 8ml, this would be x, ly squared. So the energies are a sum of the energies in the two dimension, and the wave function is a product of the wave functions in the two dimensions. So you could take a partial differential equation if you can separate the variables. And the key was back here, the only reason we could separate them is they didn't have a potential energy that was a function of x and y. We'll talk about that later, but not all partial differential equations can be separated, but this particular one can, which makes it solvable. So this is just showing you some pictures of the wave functions, how you can have different quantum numbers in different directions. So you can have nx, anything from 1 to infinity, ny, same thing. And yeah, we can just do this one little problem, which asks us, so this is self-test 7C.3, calculate the energy separation between both quantum numbers being 2 and both quantum numbers being 1. If you have an electron trapped in a box that's a square, so that means Lx and Ly are the same. So and the length is 1 nanometer. So that means it's going to be nx and ny of 2, square them both in atom, subtract nx and ny both being 1, square them in atom, and then multiplied by h squared over 8m, and it's L squared because they're equal to each other. So we end up with 8 minus 2, which is 6. So 6 times Planck's constant squared over 8 times the mass of an electron times the length of the box squared gives you 3.61 times 10 to the minus 19 joules. Your book gives it in different units, but it's the same number as I got. So one more little concept, this was a large section, is the concept of degeneracy. So if you have a square box, it's easy to see. If this is so if you have a box that's square, it's easy to see. that if nx is 1 and ny is 2, or nx is 2 and ny is 1, you're going to get the same energy. So which dimension has more energy won't change things. But you'll have different wave functions for those two possibilities. And did I show a picture of that? No. But because you have different wave functions, that means you have different states. You have more than one function with the same energy. And so it creates degeneracy, where more than one state has the same energy. It's usually a result of symmetry. In this case, a box that's square instead of unequal sides. But you'll run into that, and I'm sure you already have run into that in other classes. So that is it for translational energy. We still have rotational and vibrational energy, and then we'll be done with all the basic problems in quantum.